Hello everyone, let's recall what we learned in our last lecture video when we discussed the difference between groups and periods. A group refers to a vertical column that you find in the periodic table, while a period refers to a horizontal row. So in regards to groups, whenever you look above, you're going to see a number like this, where you'll have a regular number followed by a number and a letter. All right, there are a total of 18 groups. So the regular numbers that you see above each column is the actual number of the group, while the number with a letter that follows it is in reference to how many valence electrons there are. Remember what valence electrons are. They're the outermost electrons in the outermost energy level ring that atom is currently using. While periods, and again you can see over here there are 7 of them, each period refers to then how many rings or energy levels that particular atom is using. So anything in the first row, such as helium and hydrogen, will only use 1 energy level. Anything in the second period, lithium, beryllium, boron, all the way over to neon, would use 2 energy rings, and so forth, all the way down to the 7th. There are only 7 possible energy level / orbitals / rings. One other note that we said, groups 8, 9, and 10, all will have only 8 valence electrons. And then when you hit group 11, you restart at just 1 valence electron. And then group 12 will have 2, etc. till you get back to 8 over here in 18. Now that we have that information in our heads, let's put it to good use in drawing what we call electron configurations. All right, so what are electron configurations or energy level diagrams? What they do is they help us visualize the electrons that an atom or element has, and then helps us also interpret, am I looking at a stable, a happy, or an unstable element? That's the key, all right? And that helps us understand how that element's going to behave when it's in the presence of other elements. So an energy level, once again, is a region where the electrons are going to travel around the nucleus. Remember, they're traveling very quickly, too, near the speed of light, all right, in each energy level. All right, each level that you're using, it doesn't matter if it's number 1 through 7, but each one can only hold a certain number or maximum amount of electrons based on how large the actual ring or energy level is. So we're going to follow just a couple rules here. So the first ring, the first energy level, can hold no more than 2 total electrons. That's it. So you would draw only 2 little dots or 2 electrons on the first ring. The second energy level can hold 8 total electrons. All right, no more than 8. It can hold less, but no more. And then for our purposes, we're going to stop at the 3rd energy level, even though you can go up to 7. But for organic chemistry, we're going to do just fine with just using 3 energy levels. The 3rd one, even though it's bigger, can also hold only 8 electrons. All right, so we're following the 2-8-8 rule, is what we call it. I'll bring that up right here. So all energy levels that are being used, so no matter which one it is, 1st, 2nd, 3rd, 1st only, 1st and 2nd, 1st through 7th, doesn't matter. For an element to be considered stable, every energy level that element is using must be filled completely. And we call this, again, the rule of 8. The only time it doesn't apply is where you have elements like helium or hydrogen, where they have no more than 2 electrons. They're never going to need 8 to begin with. They only need upwards of 2 to fill that first ring. So, but for every other element, this rule of the 2-8-8 will apply. So, for example, let's say we have an element that has 8 total electrons. We're going to put 2, so we would put 2 little dots for electrons in the first energy level, and then we would put, again, the remaining 6 electrons in the second. So we're going to have 2 in the first, 6 in the second. Is this a stable element? What do you think? The answer is no. I was going to try to trick you there by writing a Y. Absolutely not, because what's happening is, and this is what I would expect you to write in a test, not just go, no. I want you to tell me no, because either you could say the outer energy level, which is the second one, is not filled. Or you could say that it's missing 2 electrons. It only has 6 in the outer energy level. It needs 2 more to make 8. I want you to be able to tell me why it is or is not actually stable. All right, so again, let's keep that 2-8-8 rule in our heads. All right, so once again, we're mainly focused on the valence electrons. All right, so happy atoms or elements are going to be stable ones. And again, the atoms are only stable when their outermost energy shell is filled. So if we look at I'll say A right here. We have one that has we have an element here that has 2 rings. All right, we have number 1 and number 2. There are 2 electrons in the first ring, so we filled that other ring. And then the dots that we have here, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons in the second energy level. This is a stable atom, so this one is going to be really happy. The next example, B. This would actually be helium. It only has 2 electrons, helium. You're using 1 ring that has 2 electrons. This again would be a happy, just kind of look at a weird little eye there. Another happy atom. And then the last one on the right here, let's call it atom C, is using 3 energy levels. 1, 2, and 3. And if you look at all the numbers, again, 1, 2 fills the first energy level. Then we have another 1, 2, 3, 4, 5, 6, 7, 8 electrons fills the second. And then we're also using the third. 1, 2, 3, 4, 5, 6, 7, 8. We're also filling this outer valence shell. So this guy is going to be really kind of creepy happy at that one. All right, so all 3 of these are examples of fully stable elements depending on which energy level they're using. Is it just the first? Is it up to the second? Or is it up to the third? All right, it doesn't matter. But if any one of these examples, A, B, or C here, if they were missing just 1 electron in either for A, the second energy level, missing just 1 in the first for this one, or missing just 1 in the third, they would be considered unstable. Here's another great diagram here to show you, just using both groups and periods also. So hydrogen is in group 1, period 1. The atomic number of hydrogen is just 1, so it has just 1 electron, as you can see. All right, this would be unhappy. All right, you would say hydrogen is unhappy or unstable because it's missing 1 electron. It wants a second electron in its first and only energy level. Helium over on the far right, all right, it's in group 18, which normally means you would have 8 valence electrons, but helium's an exception. It only uses the first energy level, so it only needs 2 to become stable. Its atomic number is 2, so it's happy. You can see that it's filled. So this is a stable atom. If you look at the period 2 examples going across, you have lithium. Lithium has the atomic number of 3, so it's going to put 2 electrons in the first energy level. And in the second, it puts its lone third one right there. This is a very unstable element. It's unhappy because it is missing 6 electrons in its second energy level, or its valence shell, which is the red. Go to the next element. You have carbon. Carbon's atomic number is 6. Again, I'm just going to write 2 electrons here in the first. If you already put 2 down, once you move to the second, you only have 4 left to get to 6. You could see those 4 dots for electrons in the red ring. Well, that's not 8. So carbon is also unstable. Fluorine, all right, in group 17, it's going to have 7 valence electrons. All right, so you put 2 in the first, and then you have the remaining 2, 4, 6, 7, all right, in the second. So I guess it has the atomic number of 9. It has 2 in the first, all right, 7 in the second. It's missing 1. I'll just draw the missing 1 as a big empty circle right now. So again, this is unhappy. See the trend here? most are unhappy unless you are in group 18, which we have the noble gases, and no matter which energy level they're using, they're always going to have that energy level filled. So if you look at neon right here, all right, that I'm using, neon has 2 in the first and 8 in the second. It's happy, it's stable. Drop down to argon. Argon has to use 3 energy levels since it's in the third period over here, you can say. So you put 2 in the first, I'll just write, 8 in the second, and it has 8 in the third also. All right, so for a total of what? 16, 17, 18 total electrons. It is happy because every energy level it's using, including the outer valence, is filled. And if we just look at the remainder in period 3 down at the bottom, again, doesn't matter how many energy levels you're using. If you're using up to 3 in period 3, you still got to make sure that there are 8 electrons in that third energy level. Sodium only has 1 right here, so it's missing 7. It's an unstable element. Silicon, all right, has 4 electrons, all right, 1, 2, 3, 4, and its third. It's missing 4 more, so it is also unhappy. And then chlorine has the atomic number of 17, so 2 in the first, 8 in the second. Just like fluorine, it has 7 outer valence electrons. 1, 2, 3, 4, 5, 6, 7, but it's missing just 1 more. So it also is unstable. All right, hopefully that's pretty clear to you now as we're progressing. So let's work on some problems. All right, here's 2 examples. Let's do one together first. All right, draw the electron configuration of an atom with 10 electrons and tell me if it's stable or unstable. So I have 2 images down below. If you're drawing these by hand, starting from scratch, only draw the rings that you need to use. All right, so I don't know what element it is unless I'm using my periodic table. I know what it is because I've done this a million times. But this element or atom has 10 electrons, so what that means is I can put 1, 2 in the first. I like to pair mine up. It's just easier than spreading them around the count. And then I'm going to go to the second energy level where I have to put 8 more because I already put 2 down. So let's say 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 2 makes 10. Again, you do not need to use the third energy level, so this is a stable and happy element. And again, it's stable because its outer valence shell, the second shell, is filled. And the second example, draw me an electron configuration of an atom with 16 electrons. And then again, tell me if it's stable or unstable. So for here, I'm going to put, again, 2 in the first. Then I can, since I'm over 10 total electrons, I can go and immediately put another 8 in the second. Hopefully you see that quickly. If you have at least 10 electrons, you can fill both the first and second energy level immediately. So 2, 4, 6, and then 7 and 8. So I've now filled the second energy level. 8 plus 2 is 10. I have 6 more left to go. So 1, 2, 3, 4. You can put them really anywhere you want. 5, 6. All right, is this a stable or unstable element? The answer is unstable. And the reason why it's unstable is it's missing 2 electrons in its third energy level. It wants 2. You don't have to do this on yours, but I'm just drawing the missing 2 that would have right there to be considered stable. So again, this second example, the atom would be unstable because it's missing 2 electrons in its outer valence shell, or you could say its third energy level, which is the valence shell itself. All right, hopefully this makes sense to you, and now you can take this information and apply it to your homework. Thank you very much again.